In this class we are going to discuss about the how to design a mux. A multiplexer is also called as a data selector. A multiplexer in short form it is called as mux, and it is also a digital switch. It passes one of its data input to the output. The data input selected is a function of the control input called selection lines. In the figure you can see a 2 to 1 mux is shown. A 2 to 1 mux consists of one select input, and you can see depending upon the input of A, one input is selected at the output. If A is equal to 0, I0 is selected, and if A is equal to 1, I1 is selected. And the general equation of a 2 to 1 mux can be written as Z is equal to A bar into I0 plus A into I1. And this is the truth table where you can see the data of I1 and I0 and the select input. Whenever A is 1, the I1 data is selected, and whenever A is 0, I0 data is selected. And in this slide you can see the design of 4 to 1 8 mux, and in a 4 to 1 mux there are 2 control inputs and 4 data input and 1 output. So in general a multiplexer consists of 2 power n inputs and 1 output. So you can see the general equation of a 4 to 1 mux. Z is equal to A bar B bar into I0. When AB value is 0, 0, I0 is selected. When AB is equal to 0, 1, I1 is selected. When AB is equal to 1, 0, I2 is selected. And AB is equal to 1, 1, I3 is selected. And similarly, you can see in the middle of the slide you can see 8 to 1 mux. There is totally 8 input and 1 output. There are 3 selection lines. So you can write the general equation. So depending upon the value of ABC, it varies from 0, 0 to 1, 1, 1. Depending upon the input of ABC, a particular input from I0 to I7 is selected to the output. And in the third structure, you can see a 2 power n to 1 mux, where there are 2 power n inputs and 1 output. So that power of n represents the number of control inputs. And in this, we are seeing the gate level implementation of mux. A 2 to 1 mux is shown in the topmost part. There you are using 2 AND gates, 1 OR gate and an inverter. The inverter is used to invert the select line, so that you can select the data when A is equal to 0 and A is equal to 1. And in the next bottommost, you are seeing the structure of a 4 to 1 mux. The 4 to 1 mux consists of 4 AND gates, 2 inverter and 1 OR gate. So depending upon the value of A and B, one particular input is selected. And in the rightmost side, you are seeing the implementation of 2 to 1 mux and 4 to 1 mux using NAND gates. Cascading multiplexer. So how to cascade a multiplexer? So if you want to construct a multiplexer of size 8 to 1, you can cascade to 4 to 1 mux, and finally it can be combined using 1 2 to 1 mux. So the structure shows an cascading of multiplexer, and in the next structure similarly 8 to 1 multiplexer can also be cascaded with 4 2 to 1 mux, and finally combined with 1 4 to 1 mux to form an 8 to 1 mux. And here we are seeing I0 to I7 represents the data input, ABC represents the select line, and Z represents the output. Demultiplexer. So the demultiplexer is also a digital switch. It performs the reverse operation of a multiplexer. It routes a single data input to one of the many outputs. So here the input is 1, the output is many. So the type of output depends upon the select line. So similarly the same design for a 1 to 8 mux, there are 3 select lines. So whenever the value of 3 ABC is 0, 0, 0, Y0 output is selected. Similarly, when ABC is equal to 1, 1, 1, Y7 is selected. There is another combination logic block that is called as decoder. Decoder is also a logic circuit that converts coded input into coded output. So each input code produces a different output code word. There is one-to-one mapping between the inputs and the output. So the structure, so it is in general we can call the size as n to 2 power n. So n to 2 power n in the sense there can be 2 to 4, 3 to 8, 4 to 16 decoders. Right? Generally it is a decoder is otherwise called as an min-term generator. Here in this slide you can see the structure of a 4 to 10 line decoder. It is otherwise called as an 4 to 10 line decimal decoder, or it is called as a binary to decimal converter. So here there are 4 inputs totally A, B, C, D, and 10 outputs 0 to 9. So depending upon the binary input, the corresponding decimal number is selected at the output. So if it is 101, if the data input is 001, first the second the number which is output represented as 1 in the output is selected. So in the truth table it is explained in clear. So here, since the gates are implemented using NAND gates, we can get an active low output. So when the input is 0, 0, 0, the corresponding output will be 0. Similarly, when the input is 1, 1, 1, so here only 9, up to 9 is valid. So when the input of 10 is obtained, the defaultly will get all the output as 1, 1, 1, 1. So when the input is 1, 0, 0, it represents 8. So the 8th output becomes 0, and the remaining all are 1. And there is also an IC available for an decoder. The number is 7442. And here it is also an NAND based decoder, so that you are seeing that all the outputs are taken out of a bubble, that is we are getting an active low output. And here here the size of a small 2 to 4 decoder is shown. So we know already 2 input, 4 outputs. And here it is there is one enable input included. This is an optional input. Whenever the enable input is enabled, the circuit works, otherwise it will not work. So here in the table we can explain the operation. When an enable is 0, no outputs are selected. When enable is 1, and depending upon the select input, the particular depending upon the input, not here we cannot call it as a select input, depending upon the input, the particular output is selected. So when the enable is 1 and input I0, I1 or 0, 0, Y0 is selected. When enable is 1 and the input is 1, 1, the output Y3 is selected. And in this slide you can see the structure of a 3 to 8 decoder. So we know that 3 inputs and 8 outputs. So the input is ABC, and outputs there are Y0 to Y7, each represent one min-term of the particular input combination. And here the structure shown is not a NAND based circuit, so that the output, the input which is given at the input, that is if ABC is equal to 0, 0, 0, Y0 is selected. If ABC is 1, 0, 0, 4 is selected, 1, 1, 1, then 8 is 7 is selected. And here the structure is shown without any enable input. And here also it is an 3 to 8 decoder circuit using IC. The IC 7X138 is a binary decoder which accepts 3 input and produces 8 output. And here it shows the gate level implementation of decoder, 1 to 2 decoder. So there is 1 input and 2 outputs. So the next one, this is an active high. If active low, the rightmost side we are showing an active low decoders. And the bottommost one shows a 2 to 4 decoder. Here we know that 2 input and 4 outputs. That is S1, S0, sorry, input, and similarly 0, O0, 1, 2, 3 are outputs. And the rightmost side represents the same criteria with active low enable signal. And here we are having an enable signal G. Decoder as a general purpose logic. So here the general decoder is n to the power n decoder can be implemented using n variables, with the variable used as the input, the appropriate min-term sum to form the function. The decoder generates an appropriate min-term based on the control signals. Similarly, encoder is also another combinational block. Encoder performs a reverse operation of a decoder. The simplest encoder to build is an 2 power n to n encoder, and here there are 8 inputs and it produces 3 output. And 8 to 3 encoder is also called as an octal to binary converter. Similarly, 4 to 16, 16 to 4 encoder is available, which is called as a decimal to binary converter. And in priority encoder is also available, and here the structure shows is an 8 to 3 priority encoder. So here, depending upon the priority, I0 will be given the most highest priority. Similarly, the bit which is given highest priority will be considered first, the remaining will be considered later. So there are still more many problems and combinational logic blocks involved, so we will discuss in the next class.